the main question that I'm here to explain, of course, or to answer today is what have I been doing in the past 5 years? And a very broad answer to that question is, well, I've been doing research on programming languages. And so the first question that comes to mind for some of you probably is, what is a programming language? So basically, a programming language is a tool that a developer uses to build computer programs. And as is the case for physical tools, there's various kinds of languages that you use to tackle various kinds of problems. So you have hammer languages, lightweight, very inexpensive to run, very precise, but they're very concise in what kind of task you can use to achieve them. Then there's bulldozer languages. They're big, they're expensive to run, but you're able to build very complex systems with them. And so as a programmer, depending on which task you have to tackle, you pick a different programming language. And so the task here at hand is implementing a function which calculates the factorial of any given number. So the factorial of 3 is 3 times 2 times 1. And on the left here, you can see an implementation in a hammer language called assembler. And on the right, you can see an implementation in a bulldozer language called JavaScript. And so even without understanding the specific code, I think the sane majority of you would pick the right language to implement the factorial instead of the left. And so that goes to show that depending on which language you choose, some tasks are harder to tackle and some tasks are easier to tackle. And so the context in which I've been doing my research on programming languages is the web. So on this screenshot on the left here, you can see what Google looked like back in 1996. So back in the days when they were a simple search engine. So you would give in your keywords, send that to the server running at Stanford at that point in time. It would calculate the results, send you back a number of links to the websites that are contained in that result. And of course, over the course of more or less 20 years, the complexity of Google has changed a lot. So they still do the search engine part, but now there's AI involved and there's targeted advertisements, but there's also Google Maps, which tracks real-time GPS coordinates. There's Google Docs, which can run offline, etc. So the web has become increasingly complex over the last couple of years. And of course, this is a broad generalization, but the tools that programmers use didn't evolve that much. So back in 1996, the Google developers used hammer languages to build Google. And even though Google has become more complex, they're still using hammer languages today. And so the goal of my PhD is to basically design and implement a bulldozer language for modern web applications. So the idea is to give everyday programmer the power to build Google scale web applications. So when I say Google scale and modern web applications, the name in literature is Distributed Rich Internet Application, or DRIA for short. And so I'm going to quickly highlight what's so special about these modern web applications. So you have your Google Docs or your Facebook server here on the right, and that server runs some application logic and maintains some application state. So the application logic is what should happen if a user presses a certain button, and the application state, in the case of Google Docs, for instance, is what text is there inside your document, right? So when you connect to that server, you send a request, the server responds to that request, and what it returns is part of the application state and a part of the application logic. And so this contrasts with earlier versions of the web, where only a static part of the application state would be returned. And of course, the reasons why DRIAs return both part of the logic and part of the state is to provide some enhanced functionality. For example, offline availability. So if you look at Google Docs, there's a button you can press to go into offline mode. So let's say you're at the airport, like Guido, and you're working on a Google Doc and you're collaborating with someone. You press on the button, you go on your plane, and you can have full access to the application logic. All buttons still work. You have your application state, and you see your text, you can change it. So you're in offline mode. Of course, once you land back on the ground, you need to synchronize the changes that you made while being offline with the changes on the server. So if we're collaborating on the same Google Doc, somehow my changes need to be merged with your changes. And so of course, this might sound easy on a glance. You just merge the changes. What's so special about that? But actually, that's a very complex problem. And it's captured by something called the CAP theorem, which is a very famous theorem in distributed programming, which basically says that there's 3 essential properties to a distributed system. The first property is consistency. So nodes in a network, a node is a client or a server, always read the latest write. So what that means is that if we're both looking at the same Google Doc, we're collaborating. When I look at my version, you see the same version as me. That's consistency. The second property is availability, which means that nodes in the network are always able to read or write the state of the application. So in the case of Google Doc is available when I go into offline mode because I can always read the state and I can always write the state of my Google Doc. And then there's the last property called partition tolerance, which says that if a network partition occurs, so if the client is unable to talk to the server, for example, well then the system maintains its guarantee. So a consistent system remains consistent, an available system remains available. So those are the three properties, and what the theorem says about this is that out of these three, only two can be guaranteed. So a system can either be consistent and available and partition tolerant, or consistent and partition tolerant. And in the case of the web, partition tolerance is an essential property. The network might fail at any point in time, clients will connect and disconnect, and so basically the choice is between consistency and availability. And so the problem here is that as a programmer of these trias, if you use hammer languages, you need to tackle two accidental complexities. And the first one is that you need to manage the collocation of distributed logic and distributed state. So basically, as a programmer, I need to start determining what part of the logic needs to run on which node, and which state needs to accompany that logic in order for it to be executed. So for example, a constraint might be that all the servers in my application run 100% of the application state, or logic, and maintain 100% of the application state. Well, depending on which client I'm implementing, depending on the constraints, the parts of the logic and state differ. So maybe an offline available client would need one part of the application state and application logic. A client with security constraints needs another part of the state and logic, etc. And so as a programmer, you're left implementing a heterogeneous network of nodes. Heterogeneous on two levels. First of all, there's different hardwares. So there's clients, there's servers. Those are different hardwares with different capabilities, different constraints. And heterogeneous, of course, because technically each node in the network might run a different part of the application logic and maintain a different part of the application state. So that's one complexity that you need to tackle if you use hammer languages. The second complexity comes from managing multiple synchronization mechanisms. So I explained the CAP theorem as if these properties apply to the system as a whole, but it's a bit more nuanced than this. These properties apply to individual pieces of data. And so you can have multiple synchronization mechanisms within the same application. So for example, a constraint might be that the servers need to be consistent. If one server writes the state, all other servers must read that latest write. While another constraint might be that your client must be available, so client must be able to go offline. They might temporarily read a different state than the one on the server, but that's fine as long as at some point they become consistent again. And so again here, the challenge is heterogeneity, so you have all these different synchronization mechanisms, all these different nodes running different kind of the application, different parts of the application logic. And as a programmer, you need to make sure that the overall semantics of your application still makes sense. And so what I did in my research is trying to hide away this complexity for the programmer by designing a bulldozer language in which these things, the programmer doesn't need to take care about these things. And so the context in which I've been doing my work is an industrial one. So I'm funded by Innovis, which is a Brussels funding agency, to something called the Doctiris program. The idea of the Doctiris program is to facilitate the transfer of knowledge from academia to industry and the transfer of real-world use cases from industry back to academia. And in my case, the industrial partner is Emixis, but I'll come back to that later. And so concretely, what that means for me is that one day a week, I sat at Emixis, we developed applications together. I gave talks about academic topics and academic research, etc. So to give you a brief overview of the rest of my talk here. So in part one, I'll dive deeper into the problem statement and the approach. So our bulldozer language, which we call triumvirate. In part two, I'll give you a brief hint at what it's like to program applications in my language. And then I'm going to end with some words on how we synchronize state in our bulldozer language called Trinivert. But first, coming back to the Emixis case. So Emixis is Brussels-based. They do fleet and workforce management. So that means that their clients own fleets of vehicles and employ groups of workforce of technicians, for example. Of course, it's a bit more complex than this. So I'm going to brutalize Emixis a bit, but that's the high-level overview. And so what they provide to their clients is dashboard functionality. So basically dashboards that give a comprehensive overview of the state of your fleet or of your workforce. So in the case of the fleet, for example, these are GPS coordinates, of course, fuel level readings, speeds, etc. And in the case of the workforce, the technicians, it's lists of jobs to be done, picture of a specific job, a schedule, etc. So the way this is implemented today is using a microservice architecture. So basically there's a central server running different microservices, and then there's three kinds of external agents. So on the left here you have the fleet, so the trucks that upload data via beacons. At the top here you see the icon for technicians, which are working in the field and have a smartphone with the Emixis application installed. And then the last external agents are dispatchers sitting behind the desk looking at a web view. And so of course this system is a distributed rich internet application. So each node in the network runs its own application logic, maintains its own application state. And the major difference is the way that they synchronize state. So in case of the trucks, every second they copy over their data to the server. So the state synchronization is unidirectional, and it's the simplest form. So every second they copy over their data to the server. Once that data arrives at the server, these microservices are automatically going to react to the incoming of new data. So each service knows there's new data that came in. I need to recompute something, I need to update my state. So this is still unidirectional, but it's a bit more complex than the previous one because these microservices need to know when to react to changes. And then finally there's the technicians and the dashboard. And so the technicians, they're in the field. They might be in situations where connectivity is not ideal. And so the application must be running, or must be able to run in offline mode. So for example, they must be able to view their list of scheduled jobs. And the dispatcher has a view of that schedule as well. So that means that they can both change the schedule. And so state synchronization here is bidirectional, so there's an arrow on both sides of the link here. And so from this example, and from what we know from prior work and from related work, we distilled 4 requirements that a distributed programming model should adhere to in order to support the development of DRIAS. So basically there are 4 requirements that a bulldozer language for web applications should fulfill. And the first requirement is that the model should provide modular abstractions for distributed logic. So as I said, each service runs its own application logic, but as a programmer, I do not want to implement that application logic from scratch for every node. What I want from my model, or from my language, is that it provides generic abstractions. For example, a generic abstraction for microservices, which I then instantiate per specific service. The second requirement is that the model guarantees data consistency properties as specified by the programmer. So coming back to the technicians, they're in the field, they might be working in offline mode. When they come back online, their state changes need to be merged with the server. And so that's a consistency model that is known as eventual consistency. So again, the CAP theorem is a bit more nuanced in the sense that it's not a binary, it's a spectrum, hence the cover, of course. So eventual consistency is in between availability and consistency on the CAP spectrum. And as a programmer, trust me, you do not want to implement eventual consistent state synchronization manually. This requires domain expertise in distributed systems, domain expertise in your domain that you're tackling. So what you want from your programming model, or your programming language, is that you just specify all the data from technicians should be eventually consistent, and the model should take care of the rest, so the synchronization itself. The third requirement is that the model should support multiple parameter passing semantics. So when you look at the job service, for instance, there's 4 points where data either enters or leaves the service. And as a programmer, what that means is there's going to be 4 points in the application logic that are polluted with either serialization or deserialization code and with bookkeeping code. So the consistency models I talked about, they typically require a lot of bookkeeping in order to be correct. And as a programmer, you need to make sure that that bookkeeping maintains correct as data enters or leaves services. And of course, as your application grows more complex, a lot more of these points arise. So what you want from your model or your language is that data automatically gets serialized and deserialized, and that bookkeeping information is automatically kept correct. Then the final requirement is that the model should allow for extensible parameter passing and state update semantics. So let's, for example, assume that Mixis wants to implement a new functionality. So the technician's smartphone now must have a panic button, which once pressed sends an alarm message to the nearby ambulance service. So as I said, the data for technicians is eventually consistent, and that's not the consistency model that you want for this new feature. If the technician has a problem, he presses the button and the application says, okay, help is on the way, stay put. You don't want that message to eventually arrive at the server if some synchronization happens. No, that message has to arrive immediately or not, but if the notification is sent out, then it must arrive at the ambulance. So that's a consistency model known as a strong consistency generally. And as a programmer, I do not want to implement this new model from scratch because it was not contained in my language previously. I want the language to provide me some ways of extending its existing semantics to be able to implement custom ones. So these are 4 requirements for a bulldozer language for the web. And at this point, some of you, or the programmers at least, probably are wondering, well, can't you do this in language X or language Y? And isn't there some state-of-the-art which already does part of this? And so, of course, as part of my research, I went through the related work in distributed programming, distributed reactive programming, data consistency models, etc. And I distilled all of my findings in 2 tables, which you can find in chapter 3 of my PhD. You can also find the relevant in various chapters. So, for example, distributed reactive programming. So this general area of programming languages is in chapter 5, for example. So these 2 tables are basically on the upper side programming models or distributed programming models in general. So these have been implemented in various languages under various forms. And the table at the bottom is programming languages that are specifically for web applications. I'm not going to go through the exact state of the art, but the idea here is that today, as a web developer, there is no technology that I can pick which meets these 4 requirements. So basically, whatever technology I pick, there's always a hammery part of the language. No language is completely bulldozery. And so that's the thing I set out to do, to create a bulldozer language which tackles these two problems of collocation of logic and state and synchronization mechanisms by creating new abstractions which hide them as much as possible from the programmer. And so the idea behind triumvirate, as the name implies, is that there's 3 data types. The programmer uses the data type to specify which kind of distributed state they want, and which kind boils down to what parameter passing semantics the programmer wants and what state update semantics are needed. So is it uni or bidirectional state synchronization, and what kind of guarantees does the data type provide with regards to the cap here? So what I'm going to do now is I'm going to go through the triumvirs, the data types, before highlighting how these are used to implement applications. So the first triumvir is called duplicable. As a programmer, if I want to implement duplicable state, I extend the duplicable class. I can then provide some fields and some methods, so this is a traditional object orientation. The idea is that if the node on the left here has a duplicate, so an instance of duplicable states, you can send it to the node on the right, and what happens in the background is that all fields and methods are copied. So for the programmers amongst you, this is standard pass-by-copy semantics, which are used for the state update semantics as follows. So if the node on the left updates its duplicate, this does not impact the node on the right, and vice versa. So this is 100% available, 0% consistency. This is the crudest form of distributed state. The second triumvir is called derivable. So the way that programmers create derivations, so instances of a derivable state, is a bit different. You basically must derive new state by applying functions to old state. And so even probably to the programmers among you, this sounds rather cryptic, and I'll come back to that later. But for the moment, you can think of derivables as an instance of reactive programming, which is a programming paradigm mostly used in user interfaces, but which we apply, and we're not the only ones, to distributed systems. And that works as follows. If the node on the left has a derivation, so an instance of derivable state, you can send that to the node on the right. What happens is that the node on the left is going to keep a reference to whom it sends that derivation to. And this happens transitively. And so what happens in the background is that there's going to be this distributed dependency graph built up by triumvirate, which is used as follows. If the node, the original node, updates its duplicate, or its derivation, sorry, then this triggers an update for all derivations that have been transitively passed along that dependency graph. This provides you unidirectional state synchronization, and with regards to the CAP theorem, it's eventually consistent, but that's a technicality which I'll come back to in the last part of my presentation. And then finally, the last triumvir is called replicable, and as was the case for duplicable, programmers create replicable states by extending the replicable class, providing some fields, and providing some methods. So if the node on the left has a replica, so an instance of replicable states, it can send that to the node on the right. And what happens is that there's a copy of the fields and the methods, but the node on the left and the node on the right are going to keep neutral pointers to each other. The way that is used is that if the node on the left updates its replica, this automatically triggers an equivalent change for the node on the right, and vice versa. And so the CAP theorem obliges. There's various flavors of replicas. There's two built into triumvirate. There's eventual replicables. So the node on the left and the node on the right are always able to read or write the state of the replica. That means that they might be inconsistent if a network partition occurs, but eventually triumvirate guarantees their consistency. And then there's strong replicas. So the node on the left and the node on the right are not always able to read or write the state. For example, if a network partition occurs, but if they're able to read the state or write the state, they're sure that it happens consistently. And so these are the three triumvirs. And triumvirate in general, as I said, it's a bulldozer language. It's implemented on top of Spiders.js, which is a library with the actor framework, which I'll come back to later, that we implemented as well. But the idea, of course, is that triumvirate implements or meets these four requirements that I discussed previously. And today I'm going to focus on requirement 2 and requirement 3, so the one about consistency guarantees and parameter passing semantics, which we solve with those three data types, those three triumvirs. And so there's two sides to the triumvirs. One side is the programming API, so as a programmer, how do I use these data types to build my application? And then there's another side, the runtime side. How is states kept synchronized between all of these different data types? And so in the case of replicables, we rely on the vast state-of-the-art from the database community and from the programming community, the programming language community more recently. So we rely on CRDTs and the global sequence protocol, two-phase commit and far references. But in the case of derivations, there is currently, or there was currently, no synchronization algorithm which met our requirements. And so we had to develop our own one called QProp, which is the topic of the third part of my presentation. And I'm first going to try at least to give you an overview of what it looks like, what it feels like to program applications in my language. So as I said, it's based on something called the actor model, which is not our invention. It dates back to the 70s. And it's basically a programming model for distributed and concurrent programs. More specifically, we use the communicating event loops flavor of the actor model. So basically, an actor is something that runs on its own thread of control, and it doesn't share any memory with other actors. So each actor has a heap of objects, and it's able to do two things. The first thing is that actors are able to exchange objects from one heap to another. And the second thing is that actors are able to change the state of objects that reside in their own heap. And so as a programmer, if I want to implement an actor, and you have to think about the fact that these actors, they might be running on different machines, on server and client, etc. So it's a modular abstraction. As a programmer, if I want to implement an actor, I extend the actor class, and I can provide some fields and some methods. In this case, the init method, which is a special case method which is invoked whenever an actor is instantiated. So these actors, they communicate using a topic-based publish-subscribe system. So the producer actor here at the top can publish the string bonjour under the topic French. And the consumer actor can subscribe to the topic French. And every time something is published, this callback here is going to be invoked with a copy of the message that was published. So that's a straightforward example. So let's make it a bit more complex. Let's say that messages are no longer simple strings. They should be objects that contain the timestamp when the message was created, as well as the text. So this typical use case for duplicable state. State just needs to be copied from one actor to the other. There is no state synchronization involved. So the programmer extends the duplicable class. So a message contains a timestamp and some text, and then there's an initializer for the state, and that's it. So the producer actor instantiates a message with a certain text, publishes the messages under that given topic. The consumer, of course, subscribes to that topic, and this callback here is going to be invoked. So this message variable here is going to be bound to a duplicate of the original message that was sent by the producer. And so the takeaway from this slide here, of course, is that if the producer changes the text of his message, this has no impact on the duplicate received by the consumer and vice versa. There is no state synchronization between them. So a bit more complex example, let's say we want to implement a like counter. So typically on Facebook, if I'm looking at a post and I hit the like button, and somebody in North America is looking at the same post, he might not see the like immediately. That's not just network delay. My phone is probably talking to some data center in Northern Ireland. His or her phone is probably talking to a data center in North America, and there is some synchronization happening behind your back, and that typically is eventually consistent. And so if you want to implement your like counter in Triumvirate, what you do as a programmer is you extend the e-replicable, eventual replicable class. So your counter has a value, how many likes have been given, and there's a method here, inc, which increments that value. And the interesting part, of course, is on line 4, this add mutating annotation, which a programmer uses to signal the Triumvirate runtime that every time that method is invoked, the state of your like button of your counter changes, and so there must be some state synchronization between all replicas. So the producer actor can instantiate a new counter, publish that counter under the given topic. The consumer, yet again, subscribes to that topic. And this callback here, this CNT here, is going to be invoked with a replica of the original counter sent by the producer. So what that means is you could have two machines, so these could be two separate machines on the other side of the world. They both have a replica of the counter. They can increment the counter concurrently, even while being offline. And when they come back online, automatically Triumvirate ensures that the state is consistent. And so the important part of this slide is all the things that you're not seeing. What you're not seeing is serialization and deserialization. What you're not seeing is the programmer instructing that every time inc is invoked on the right, there must be a message sent to the left saying, hey, I changed the state, please keep it consistent. All of this is done by the Triumvirate runtime. So all of this is done by our bulldozer language. Okay, so now we have eventually consistent counters. Let's say that we don't want eventually consistent counter, but strongly consistent counter. So if you're looking at the same post as I am, and we're looking at our like counter, if I see that the like counter is 5, you should also see that the like counter is 5. So the only thing you need to change compared to the previous code is instead of extending the e-replicable class, you now extend the s-replicable class, strong replicable. And for the rest, the code remains the same. Or at least the code remains the same lexically. So the devil, of course, is usually in the details. There's a big semantic difference between this code and the previous code. And the semantic difference is not syntactically visible, but it's this dot operator here. So in the previous slides, all operations are available and synchronous, so you can always read or write the state of your replica. And this is no longer the case. Inc is only going to be invoked if Triumvirate can guarantee strong consistency. So if you're offline, invoking inc is not going to have an impact until you come back online to ensure that the state always remains consistent. And so again here, the important things is everything that you're not seeing, namely the fact that the programmer doesn't need to care about this. All of this is hidden away by the Triumvirate runtime. So as a final example, I'm going to take a bit more of a different example. Let's say that the producer should act as a clock, so it produces values on a regular basis, and the consumer should read a value from some external sensor every time a new value is produced by the producer. So this is typically something we would call a reactive program. You have one part of the state of the system that changes, that reacts to changes made by another part. So every time the producer changes, this should trigger a change for the consumer. So that's a use case for derivables. So each actor has a built-in derivable called this.seconds, which every second produces a new value, namely the latest wall clock. So the producer publishes that derivation under the time topic. The consumer subscribes to the time topic, and this callback here is going to be invoked with a derivation. So stream is going to be bound to a derivation of this.seconds. What that means is that every time this.seconds changes, that stream variable that could be on the other side of the world changes as well. And so the consumer uses this to read values from a sensor by applying a derive function. So basically there's a callback here invoked with the stream, and every time stream changes, the callback will be re-invoked as well. So the value of the sensor will be read again. And so the important part again here is everything that you're not seeing. So what happens in the background is that Triumvirate creates a dependency graph from this.seconds to stream to this callback here. So every time the seconds changes, every time the clock ticks, stream updates. Every time stream updates, this callback here, or this statement here is going to be re-invoked, thereby updating the value of sensor vals. And if the consumer again publishes that data to another actor, this again updates the other actor. No matter where they are on different machines, different side of the world, etc. So okay, the programmers among you probably think, well, yeah, that's cute. You implemented 3 toy examples in your language. How is that a bulldozer language, right? And so, no, I'm not there yet, actually. That's the next slide. So that was one part of my PhD, coming up with those data types. A different part, of course, is how do all of these different data types coincide inside one single application. So there's 4 laws that govern the interaction, and the idea of those laws is to prevent the programmer from making mistakes, so introducing bugs that would break the guarantees provided by the data types. So we're going to quickly highlight the last of these laws. So the activity-reactivity isolation law, which is a large name, okay. So there's 2 kinds of state in triumvirates. There's active state and reactive state. So active state is mutated by the control flow of an actor. If you think back to our counter example, there's an imperative statement in the inc method which updates the state of the counter. And this contrasts with reactive state. If we think back to our sensor example, at no point in time did the programmer have to imperatively change the state of this.seconds or of stream or invoke the callback. All of this is declaratively specified, and Triumvirate handles the rest. And so Triumvirate ensures that programmers do not start mixing and matching this imperative code with declarative code by disallowing the creation of dependencies from reactive states to active states outside of the derive function. And so what happens is if the programmer makes a mistake against that law, then a runtime exception is thrown, informing him or her of the mistake that he made. So now I come to the part about how it's cute that I'm able to implement 3 toy examples. So you're probably wondering what the hell I'm doing with my phone and how this works. So basically, these are not slides. This is a distributed rich internet application. So I invite you all, mobile or desktop or laptop, to go to the following link. And if you go to that link, what happens basically is that your mobile device is going to send a request to a server that I'm renting in Ireland, and that server returns part of the application logic and part of the application state of my presentation. And so what that means is that there's 3 kinds of states in my system here. There's the slides, of course. So when you go to that link, you'll be able to follow the slides on your mobile device. And that's implemented using a strong replicable, which means that I guarantee that if your mobile device asks on which slide we are, that we're always looking at the same slide. Unless you're offline, of course, and in that case, you don't get a return. So that's one feature of this keynote presentation here. The other data type, or the other piece of state and logic that we have are questions. So at the top here of the slide appeared an icon, which you can use. So you should be able to click on that on your mobile device as well. Somebody beat me to the punch. But, so you can ask questions. I'll ask the first one. Does it scale? Of course. You can submit that, and you can vote for some programmers in the room, of course. So you have 2 votes that you can cast for specific questions. And so that part of the application functionality is implemented using an eventual replicable. So what that means is that if you go offline, you can still ask a question, you can still vote for a question, and when you come back online, the state is synchronized. And then of course there's a last part of this functionality here, which is the pointer. The pointer you've been looking at, which is of course implemented using a derivation. So I'm not going to dive into the code, but the idea is that when I connect it to my server initially, I have a duplicable that represents the coordinates of my finger on my phone here. When I connect to my server initially, I send a derivation of that duplicable to the server, and when you connect to my server, you get a derivation as well. And so when I press a button and I start dragging, this updates my local derivation. Automatically, this triggers a change for the derivation running on the server all the way back in Ireland, which automatically triggers a change on your device as well. All of this without having to explicitly say that you should now update the red pointer on Wolf's screen. All of this happens automatically. So that's the developing VIAs in Triumvirate. I'm going to quickly highlight the state synchronization part. So as I said, replicas, we rely on state-of-the-art synchronization mechanisms. For derivations, we had to implement our own. And so the first question is, how do you need to update a derivation? What's state synchronization for derivations? What is derivation correctness? And so in the state-of-the-art, this is called glitch freedom. And the idea is that you have this distributed dependency graph of derivations here. Server is lagging a bit. And the correct order, of course, of updates is the topological one. So you should, the derivation should update according to the topology of the dependency graph. So the way that this is done in the state-of-the-art, for example, in Guido Savaneschi's setup algorithm, is using a centralized server, which is going to dictate when each derivation is allowed to update in order to avoid bugs, which are called glitches in this instance. So the server is going to dictate that first the fleet service should update, then the geo service, then the dashboard service, etc. Of course, this is a single point of failure and a performance bottleneck, as well as a scalability bottleneck. And so the question becomes, can we get rid of this centralized server and still have glitch freedom? And when I try to explain this problem to colleagues or to people at conferences, the responses usually start with, we'll count you simply. So I'm going to start with the count you simplies because they're important to understanding the problem at hand. So the first count you simply is, can't you simply always update, a node always updates if it receives a new value from a predecessor. So C, I'm going to stop using pointer because it's lagging. So C should update if it receives a value at the top from A or from B, which of course in this case is not correct because the topology dictates that if C receives a message from A, it should also receive a message from B. Okay, well then can't you always make a node wait for all its predecessor to produce a new value? So C should update if it receives a new value from B and from A. And of course in the bottom part, this is not correct either because B might produce a new value, but A might produce a new value in a year, given that they're not related to a common ancestor. And so the problem is actually a bit more complex. This AND versus OR semantics depend on who's sending the value as well. So in the case, going back to our fleet management example, the dashboard service should use AND semantics if the geo or driving service produce a new value, because they depend on a common ancestor, namely the fleet service. If the job service produces a new value, the dashboard can safely apply OR semantics. Use the new value from the job service, and the new job schedule, for instance, and use the older values from the geo and the driving services. And actually, the problem becomes more complex, of course, if the topology of the network, of the dependency graph becomes more complex. So in this example, A and B might concurrently update. C might send an update to E as a result of A updating, but with the old value from B. D might send a value from E to E as a result of B updating, but with the old value from A. And then the question is, what should E do? So how should the derivation in E update, given these two new messages? So what we did is we came up with a new synchronization algorithm called qpropagation, or qprop in short, which ensures glitch-free updates. So it ensures that derivations update correctly. That if I drag my finger on the screen, your screens update correctly. without resorting to a central server to dictate when each derivation should update. So there's 3 phases. In the exploration phase, nodes are going to determine the topology of the dependency graph, given that, of course, the topology is essential to solving the problem. The second phase ensures that updates only start propagating if the previous phase has finished. And in the last phase, of course, then derivations start updating and values flow to the graph. So I'm not going to go into the details of the algorithm, don't worry. If you want to go through it, it's chapter 5 of the PhD and discussed at length. But the intuition is that it allows each node in the dependency graph to, independently from the rest, and that is important, of course, determine if it should apply AND semantics or semantics and which values it should use to update itself. So we qualitatively evaluate this algorithm. So we prove that it provides bit freedom, that indeed it ensures that derivations update in the correct order. We also prove monotonicity, so nodes only update with newer values, never with older values. And we prove eventual consistency. So remember in the beginning of my talk, I talked about derivables and how they provide unidirectional state synchronization with eventual consistency. So that's a technicality which stems from our use of QPOP to update derivations. So of course there's a qualitative evaluation, there's also a quantitative one. So we benchmark our approach against a state-of-the-art centralized one, namely Guido Savaneschi's SIDUP algorithm. So we measure a bunch of different measurements, we did a bunch of different benchmarks. The most telling one is the throughput benchmark. So throughput is a number of values which populate from source to sink for a given period of time. And so on the x-axis you have the load, so the amount of requests per second coming in at the server. On the y-axis, the throughput measured, so how much requests per second is the server able to handle. And we highlighted 3 different, so higher is better. We highlighted 3 different points in this graph, and those are the weekend, evening, and daytime loads measured at TMX's production system. What you can see is that the centralized approach, so the orange one, is able to handle evening loads and then it tops out. So it's able to handle 100 requests per second and nothing more. While the decentralized approach, so our approach in blue, is able to scale up to the daytime load at ease. So we were able to handle 300 requests per second. And for the given hardware, of course, we're able to scale up to 700, 800 requests per second before the performance starts to decrease. So that concludes the main part of my presentation. So what I presented today is Triumvirate. It's a domain-specific language built on top of our Spider.js system there. It meets those 4 requirements for a bulldozer language for web application, which I discussed in the beginning. I didn't discuss requirement 1 and 4 in detail, and the reason is that these are actually trivially met if you have a decent actor system with a decent meta layer. So when I joined the VUP in 2009, the Software Languages Lab was using actors and meta layer technology, well, way before I was there. And the reason this is still a requirement today for the web is, of course, because the web has been running behind on what is the state-of-the-art in distributed programming. So the important or the interesting requirements are requirement 2 and requirement 3, which we solve using those 3 data types, those 3 triumvirs. So that's the triumvirate, the software artifact, and kind of the vision as well. But of course there's contributions, concrete contributions to the state-of-the-art that underlie my PhD as well. So each contribution is supported by a major publication, highlighted in bold, in either a peer-reviewed journal, conference proceeding, or a book chapter, as well as a number of supporting publications. So these are either workshop publications or conference publications where I'm not the first author. So these first 2 contributions I discussed today. So that's our algorithm for derivation updates called QPOP. This idea of letting programmers explicitly choose what kind of distributed state they want to implement by having different kinds of data types. So I discussed 3, and there's actually a meta layer to Triumvirate which allows you to extend it to add more. And then there's the last contribution, Actors for the Web. This is Spider.js system, which I didn't discuss. And the idea is that the web has been using this actor technology for quite a while. So Node.js, for example, could be seen, or the event loop in Node.js could be seen as a big communicating event loop. But so far, it's only been used as a runtime technology. And so with Spider.js, we marry the programming API with the runtime technology. So as a programmer, you program against an actor API, but these actors also map to runtime actors. So a triumvirate actor is a web worker in the browser or a child process on the server. So that concludes my talk as a whole. So what I'm going to do now is first answer, of course, the questions from the jury members, and then I'll go through the questions that you asked in hope that the server is still in hope that the server is still live. I hope you kept it more or less decent. I know I wouldn't. So there's no stupid questions, only stupid answers. So I'm the one answering them. So make me look stupid by all means. And thank you for your attention, of course, and for being here.